So the vertical structure of the atmosphere has something very important called thermocline. As you can imagine, thermocline is a temperature gradient. What does it mean? So near the surface, let's say we are in the tropics, we have strong heating and we have warm sea surface temperatures, let's say in the range of 28 degrees centigrade at 160 west to south. So that is in the central western Pacific, just to the south of the equator. And that warm temperature quickly cools as you go deeper down to about, let's say, 100 meters or so. Below that, there is a very sharp gradient before the temperature reaches a nearly uniform deep ocean temperature of 2 degrees centigrade or so. So this gradient here is called the thermocline. If you do salinity, it'll look the opposite. You have because in the these regions there is a lot of rain, the salinity will be lower near the surface. It'll increase and then it'll become constant to the deep ocean. So that it would be called a halocline or a salinity gradient. If you mix them together, the ocean density is a function of temperature and salinity. In fact, it's a non-linear function of temperature and salinity, as we will see in a minute, and that gives you a density profile, which is, of course, density is lighter at the surface, then it'll sharply increase. Maybe we should go this way, lower, sharply increase, and constant to the depth. So that's called a pycnocline. So thermocline is temperature gradient, halocline is salinity gradient, and pycnocline is the density gradient. And as we saw, the ITCZ, sea surface temperature, everything changes in time. So you would expect the sea surface temperatures to also affect the variability of the thermocline. And there are, of course, other processes as well that affect the thermocline. So you can think of it this way. Let's say we are at a place where the winter mixing is deeper, so the surface layer is mixed down to about 100 meters. What do we mean by mixing? Basically, you have winds that are constantly churning the water, precipitation that may be stabilizing the water by putting fresher water, lighter water on top, or there could be very heavy evaporation that is removing water molecules, leaving salt behind, increasing the density and mixing that way. Or you can have heating and cooling. Heating can stabilize the surface, cooling can destabilize, create heavier densities, and so on. So let's say we are in March, where the surface mixed layer is down to 100 meters. I don't know where we want to start. So let's say we are in March. Sun begins to move into the northern hemisphere, so surface begins to warm. So you are going from 4 degrees centigrade temperature at the surface. So we are obviously at a very high latitude. Surface warms, so you begin to form a thermocline. Here there is no thermocline. It is going deep down. It can go hundreds of meters mixed well from the surface down to a couple of 100 meters. So here you have created a surface warm stable layer. So you've created a small thermocline. By July, more sunshine is available. So now you have created a much stronger thermocline or a temperature gradient. By August, the heating is maximum. So you have the strongest thermocline. And September, as the sun begins to go south, you have again cooling of the surface, so the thermocline begins to erode, so the surface mixed layer gets deeper. By November, it's much deeper, thermocline is reduced, and then by January you are down towards well mixed surface layer and the thermocline almost disappearing. So you can see, depending on which latitude you are, you can have a very strong variability in the vertical structure of the ocean. It turns out that when this happens, the deep ocean nutrients get mixed up to the surface, but there is not enough light. But as soon as the sun comes up and the surface layer begins to stratify, nutrients get concentrated in this layer. light becomes available because sun is coming to the north, so you get a big phytoplankton bloom. Photosynthesis happens, and you remember that animation we saw of the ocean chlorophyll high latitudes kicking up during spring months. That's created by these kinds of processes. Okay. And if you look deeper down to 3,000 meters, this is from Wikipedia, you can see that the surface mixed layer, where we said turbulence is generated and temperature, salinity and density are typically mixed down to be uniform. Then you have a sharp seasonal thermocline. So in the tropics you have very warm temperatures, shallow mixed layer, and a sharp thermocline. And in the mid latitudes it depends on whether it's summer. So in the summer temperatures are warmer, the thermocline is sharper. In the winter mid latitudes temperatures can get quite a bit cooler, so the thermocline is weaker, whereas at high latitudes you get hardly any seasonal variability of the thermocline. So we were looking at somewhere here in the winter temperature of 4 degrees centigrade increasing to something like 14 degrees centigrade. So we were in this range. So that's the mixed layer. This is called the seasonal thermocline because it changes with season like this. Deeper down there is something called the permanent thermocline, which is not affected by the seasonal changes on top, but we will not get into those details. But here it is the permanent thermocline. Okay, so vertical structure of the ocean is very critical for determining how much heat is being stored in the upper layer, because that's what affects the atmosphere on a day-to-day time scale. So the coupled ocean atmosphere interactions, which determine the fact that at weather time scales atmosphere is running around on its own, and weather forecast becomes chaotic after a few days, whereas if you want to integrate few weeks to few months and longer, ocean begins to control atmosphere's variability and so on. Then it's the heat that is deeper that begins to affect the exchange of energy between the ocean and the atmosphere. Okay, so that's important to remember. That leads us to the next big part of the ocean circulation. It's a very brief introduction, as I said, so you can look it up in my other courses. We have what is called thermo-haline circulation. So there are special regions where these western boundary currents bring up warm water. They create warm surface temperatures. The atmosphere above, which is able to pick up the moisture from this, is able to then evaporate the ocean. Every time you create evaporation in the ocean, only water molecules are lifted, salt is left behind, and because the water molecules are dragged out of the hydrogen bonds, breaking hydrogen bonds, waters also get colder. So there are special places like in the Labrador Sea and the Greenland, Iceland, Norwegian Sea. This warm waters coming up create heavy evaporation and deep water, so-called North Atlantic deep water forms, and it sinks like a rock, and then it also has to undergo western boundary intensification for reasons similar to the ones we mentioned before, the latitudinal variations of Coriolis effect, and it crosses the equator, comes to the south. In the Southern Ocean also there are a couple of places where deep water forms because the waters are cold enough, and there are ice shelves, sea ice formation and so on, which are able to create the densest water, which we will see in the next podcast. They also sink. So because this is a channel, the waters circulate for some time, and then they inundate the Indian Ocean and the Pacific Ocean. Those waters are slowly converted back to surface water, and then they come back. So the Pacific water that is converted to surface water comes back through the Indonesian seas into the Indian Ocean, mixes with the surface waters being converted from the deep water, and is being taken back out. Some of it cycles back into the Southern Ocean, some of it goes around Africa, mixes with the water coming from this side, and goes across the equator again to the north to fill the mass balance needed to by creating the deep water here. So the deep water formation here requires new water to come in, and that water is coming back through this upper warm branch of the thermohaline circulation. It is called thermohaline because it's temperature and salinity driven circulation, or density driven circulation, as opposed to the wind driven circulation. It turns out that it's not really independent of the wind driven circulation, but nonetheless it's easier to understand by thinking of them as two separate components of the total ocean circulation. So this is the cross-equatorial energy transport that I mentioned before. And I said the ITCZ is to the north because ocean is moving energy to the north, and the ITCZ is to the north as a energy equator. It's moving energy across the equator to the south to balance the energy that's being brought to the north by the ocean. So let me stop this here and add a few more points about the thermohaline circulation in the next podcast. But you can see the sharp salinity contrasts and temperature contrasts here. The same latitudes here, temperatures are much colder, and the salinities are much lighter. You can see the scales here. The salinity in this region is significantly higher, and because the temperature and salinity relation to density is very nonlinear, small differences in salinity and temperature can make a big difference in density. So the densities get heavier here and they sink, whereas such sinking does not happen here even though the temperatures are cold, because the salinity is not very high. Mediterranean is much more saline, so some deep water forms here as well and comes out into the Atlantic Ocean, and of course deep waters form here as well. And we'll see what are those deep waters and how we know they are deep and where they are formed and so on and so forth in the next podcast. Okay?